Our final speaker is the second trainee talk of the day, and it's Reza Khan Mahmoudi, and he is currently a second-year PhD student at Michigan State University in the Department of Computer Science and Engineering. So let's congratulate and welcome Reza to the stage.
Good afternoon, everybody. I hope you're all enjoying your time here. I have so far very much enjoyed all the talks being given here, and I hope to see and hear the rest of them. It is my utmost pleasure to be standing here right in front of all these great experts in their fields to present to you and share with you some of the advancements that we have made in the intersection of artificial intelligence, natural language processing, and the great healthcare. My name is Reza, second-year PhD student, studying computer science, artificial intelligence, and I'm here to present to you our work titled Enhancing Information Extraction from Electronic Health Records, an Iterative Prompt Engineering Approach using GPT-4 and Llama 2. So I would like the audience to raise their hand up if you have whether heard, used, or seen any of these large language models, including ChatGPT. Okay, so more than at least half of the crowd that I can be sure. So there is no doubt, honestly, no doubt that there was a revolution that took place less than a year ago. Less than a year ago. It was November 30th that OpenAI introduced ChatGPT, and ever since then, it's just been the man of the hour. So this rise and this great revolution didn't take place overnight. There was this great line of research, long line of research, starting with multi-head attention back in 2017 that led to transformers architectures, pre-trained language models, and the abundance of data. These got fused and gave birth to large language models. These models come with lots of advantages and lots of applications. They just are great at what they do, which is language and text processing. So one of the downstream tasks that we can use these models to apply to in the domain of healthcare can be cancer symptom extraction. Extracting symptoms from oncological patients' records is a complex yet crucial task. A precise extraction process is essential for analyzing patient experience and guiding effective treatment strategies. So we can utilize large language models and which could offer a practical solution to the challenge of efficient symptom extraction from cancer patients, and could potentially lead to improving the quality of oncological care. So you can see that this thing didn't just start back in 2020 or 2022, which was OpenAI's introduction of ChatGPT. This all started way back ago from language models. So this line of research, as I mentioned earlier, is basically it all starts with pre-trained models that just got improved and improved and improved by different corporations and different researchers. They all contributed to this great field, and right now we're seeing the abundance of these language models, large language models nowadays that are being introduced by Meta, Google, OpenAI, and all sorts of stuff. So in our work, we have an overarching hypothesis. Our general hypothesis is that achieving large-scale oncological toxicity extraction can be achieved through leveraging large language models, which will enable symptom extraction from oncological clinical notes at a proficiency at least equivalent to human experts. So I know that I should be cautious with that phrase, to be at least as good as human experts, because that's, well, at least we can give the room to the model to try. But in order to achieve that overarching hypothesis, we have sub-hypotheses, starting with the first one. So we did this research a while back ago that we focused on domain adaptation of these models. So here's the thing. These models, by default, have seen lots of data. But this lots of data is one thing. Asking the model, hey, this is our data. Focus on this specifically because we want you to perform some downstream task here specifically is one side of the coin. So we can perform this through fine-tuning to let the model to adapt itself to the domain that we want to apply it to. So we had this research that we focused on fine-tuning BERT, which worked perfectly And here in this paper, in this project, we are after the second step, to optimize prompt and prompting, basically, which can yield better outputs. So we ask these models to focus on this data through fine-tuning, and then we have to have this discussion with the model to get to our downstream task. And that can be achieved through proper prompting. If the prompts, literally the questions that you ask or the task that you give the model through text is not well-defined, is not optimized, the model will be in a gray area and it'll be just basically revolving around itself, wandering around, not knowing exactly what to do. The same thing happens with human. If you're not asked the right questions with the right language, you do not exactly know what you're asked for, so you do not perform well. Hence, the accuracy of you performing and executing the task will not be good. So we will be focusing here on this specifically, which will hopefully lead to our final hypothesis, which is to enhance accuracy with large language models. So these models are great at themselves. We ask them to focus on our data. We ask the right questions, literally, and hopefully this will all lead to improved performance. So, in order to introduce to you our advancements regarding prompt engineering, first I will have to say what prompt engineering even is. But before that, I will also have to explain what prompt is. Prompt is basically that text that you give to ChatGPT saying, hey, write me an apology letter to my wife because I forgot yesterday was our anniversary. And it provides you with this text, and you again ask it, I messed up big time, please make it more dramatic. That's again another prompt. So on a serious note, prompt is that piece of text that you give the model to, and that needs engineering in different ways. And what do I mean by engineering? Our objective here, in our case, is to maximize large language models' accuracy in symptom extraction by optimizing the structure and the content of questions. So this engineering has different processes. First and foremost, experts need to be in the loop. They will have to provide you with insights on how and what the right question even is to ask, because they are being asked the same question over and over again on a daily basis at their job. So they need to be in the loop. Second, we need to have an iterative refinement and development of these prompts, see how the model performed and refine it further. And standardizing the language. So if the language model is accustomed to a certain terminology, you cannot just all of a sudden shift and use another terminology. You have to be consistent with how you're basically behaving with it. And these, of course, do not come without any challenges. Large language models can produce varied responses based on the prompt nuances. The right structure ensures precision, which is one of the most important things in the domain of clinical and healthcare. So the feedback mechanism also matters. How we achieve that proper prompting is heavily based on how we see what the different effects of applying different techniques to the prompt was, so that we can better improve our prompts. And the consistency, one other issue, last but not least, consistency, which ensures that different prompts yield stable and reliable outputs, especially in the clinical context. If we ask the model the same thing again and again, will it reproduce the same thing again and again? So in this project, we are focusing on prompt engineering optimization, meaning that all of the stuff that I introduced to you in the previous slide, we are here to optimize that engineering process. Automated iterative prompt improvement by a large language model. So what does that mean? Our objective here is to see whether large language model guided prompt optimization can work, to investigate whether one large language model can be used to improve the performance of another large language model in extracting information from EHRs. So basically leaving the task of optimizing the prompt for a large language model which is executing, leave that task to another large language model. Crazy. So our method here is to use a two-model approach, which consists of GPT-4 to refine prompts for Llama 2. Llama 2, GPT-4, I'm pretty much sure everybody knows it from OpenAI. It's not open access. Well, you can access it open, but it's not for development purposes. But Llama 2 is totally open source, and you can use it. And we will be, in this project, asking Llama to ask questions, to basically extract information and toxicities, and ask GPT-4 to refine based on how it's performed. More specifically, each electronic health record undergoes 10 iterations of this refinement. At each refinement, Llama 2 generates a vector indicating the presence, the absence, or the neutrality of a post-radiotherapy toxicity symptom. So after that, after each iteration, a similarity score is calculated. All of the information is provided to GPT-4 and say, hey, GPT-4, this is how it performed on given this prompt. What do you think? How can we improve the prompt so that the accuracy improves? So in our research, we focus mainly on 10 frequent toxicity symptoms. There is different categories of them, but we have focused on 10 specifically for development purposes, and which consist of dysuria, urgency, and erectile dysfunction, and so on and so forth. So given these 10 symptoms, we give notes to the large language model named here Llama and ask it to extract information. So there are two main parameters that Llama is built on top of, which is the temperature and the top P. So these two, one of them is the creativity measure of the Llama 2, and the other one is the measure of randomness. So it's basically giving the model information about how should it behave while it's decoding the text that it wants to. So there needs to be done a search in terms of the hyperparameters that we can potentially use. So we've done so with an initial prompt, seen which one was the most stable one with respect to accuracy and precision, and then performed 3 rounds of reproducibility check to sanity check, and afterward we used these hyperparameters in our final model. So, our final model. We have a cohort of 4 patients, 10 clinical notes, which we anonymize the notes provided from Hillary Health using BERT. And after anonymizing them, we use 2 different versions of ChatGPT. 3.5 Turbo to come up with the gold standard annotations, and GPT-4 in order to be in charge of the refinement. Our objective here is to utilize prompt engineering to align Llama 2 model's outputs with GPT-generated standard values. And we use Llama 2 13 billion chat Hugging Face for our development. You can see that at the very first epoch, the average accuracy across these 10 notes, given an initial prompt, right? No refinements done, just an initial prompt. It performs around 45% accurate, and with a high variance of 0.27. And as we refined it through 10 iterations, it went up to more than 70% accuracy on average, with a less variance. So, what was our initial prompt? We asked that your task is to function as a clinical analyst, reviewing a series of electronic health records. Return me 1 if you do see this given target symptom, which is, for instance, diarrhea in this case, or give me -1 if you don't see it, or give me 0 if you either don't know or you do not see such information. So, and just return just the number. So after doing this, we extracted the symptom using large language model, in this case, Llama 2. We have this vector, we calculate the similarity score, and how good it did, we provide all the results to GPT-4. And then we ask GPT-4, hey, this is how it performed on this prompt. Can you optimize the prompt for us? At the first round of doing this refinement, we can see specific changes that took place by changing the prompt from GPT-4. You can see that it changed it such that it used a different tone. It said, you are acting as a medical data analyst, tasked with assessing a series of electronic health records. At the second refinement round, it said, acting as a clinical data interpreter, your duty is to do this and that. At the third, it says, your function as a clinical analyst, and your task will be, again, task. So it's just trying to figure out how is this thing working out. And at the 10th one, we can see that it says, first and foremost, your duty. It starts with that. Your duty, and this has been experimentally seen that the very first words, those are the ones that the large language models pay the most attention to. So it starts with saying your duty is, as a clinical analyst, is to examine electronic health records identified with da-da-da. So all these refinements are being done through different iterations, and GPT-4 is in charge of them. So to conclude, semi-automated prompt optimization using large language models, in this case GPT-4, improves radiotherapy toxicity abstraction in prostate cancer patients. This holds potential to develop an automated pipeline to extract toxicities from therapy among cancer patients. And in our next steps, what we are aiming for is first and foremost refine the large language model, because there exist lots of hyperparameters that can be played around with, that can be set properly, and there are always these models coming out on a daily basis. So in order to have this great system working out perfectly, we should be always keeping our eye on this progression of the large language models. We can establish a gold standard, which Henry Ford is generously helping this project with this, in this regard, to come up with these annotations. As you see, I mentioned in previous slides that GPT 3.5 was in charge of annotating the notes. This can, of course, be improved by using experts. And on the third step, we can validate on a large, we want to validate on a large cohort, increase the number of patients and the number of nodes, and last but not least, we can expand to other cancers as well, not just prostate cancer in this project. So last but not least, I want to thank Dr. Gassimi, my supervisor, Dr. Chen from Henry Ford Health. They have generously helped me throughout this project, whether it's 3, 4 a.m. or 11, 12 p.m. They have just been, I'm a bad student, I know. They have always been there for me. And all other great fellow from Henry Ford, I apologize in advance if I mispronounce any names, Dr. Verdikia, Ghanem, Bing, Chetty, Elshak, and Movzas. I would like to thank all of them and the very great collaboration that's been taking place between Henry Ford and Michigan State. On behalf of students, as a student of myself who is in second year PhD, I would like to thank you for this great collaboration, because I myself and all the other students here, we are taking advantage. We are being blessed with this great opportunity. We are improving in our research field. We're improving in our research. We're increasing the number of, not just the publications, but we're in a great safe place that we can increase our performance and get better in terms of research in our research field. So that's all thanks to you. And with that being said, I would like to thank you for your attention and your time.